Hello everyone. Today I'm going to be talking about some important identities that you need to know for trigonometry for the further pure math exam. And these are the identities of sine A plus B, that is the sine of two angles added together when you know both of those angles, as well as cosine A plus B. And in the next video I'll also be talking about tangent A plus B. And basically, these identities enable you to figure out any kind of sine or cosine value when you have two angles added together. And it is also useful to answer a kind of question that I'm going to talk about later, which is basically like show that sine 3 theta equals something, stuff like that. Alright, so first I'm going to tell you right off the bat that basically at the moment the two identities that I will just sort of tell you that I've memorized already is that sine A plus B is equal to sine A cos B plus sine B cos A. And secondly, it's also the case that cosine A plus B equals cos A cos B minus sine A sine B. But how do we actually get to this? How do we know that this is true? So I'm going to show you the geometric proof for both of these identities. Basically, you have one triangle here, and this is going to be your triangle with angle A. And then on top of it, like this is a right angle triangle, on top of it you have another right angle triangle. And this is going to be your triangle with angle B here. And if you want to find sine and cosine values of a right angle triangle, and you want to be able to do it by side lengths, then you know from the way you use the unit circle, like how there's your angle here and then the radius 1, then you have your x coordinate and y coordinate are sine and cosine theta. If you have the hypotenuse of a right angle triangle to be 1, and you're looking at, say, this angle here, then this side is going to be sine of theta, or rather the y coordinate of this point is going to be the sine of theta, and the x coordinate of this point is going to be cosine of theta. So the way I'm going to start off is by making the hypotenuse of this triangle with B equal to 1. Then we know that this side must be, or not cosine B, but sine B, as it is the vertical, and this side must be cos B. And we are looking for sine A plus B as well as cos A plus B. So we need to create our right angle triangle with the angle AB by drawing a line down here. So if we find the length of this line, given that the hypotenuse here is 1, we will have found the sine value for sine A plus B. And this length here is also cosine A plus B. Now, given that the hypotenuse of this triangle is cosine B, we know that this side here is not going to be 1 times sine A, but rather cosine B times sine A, because the hypotenuse is cosine B instead of 1. The entire triangle is being scaled, multiplied by an amount of cosine B. So this side here will have the length of cos B sine A. And this whole side on the bottom, this entire length here, will have a length of cos B cos A. So where do we go from here? The next step in the proof may be seen as a bit counterintuitive, but in actual fact you have to create a line from here to split this triangle into two more right angle triangles, one here and one here. And now the interesting thing is, given that this line and this line are parallel, you can use the theorem that alternate angles are parallel, which you would have learned in core GCSE, to get that this angle must be A as well. And once you know that this angle is A, you know that since this is 90 degrees here, this angle must be 90 minus A. And so this angle is A. This triangle and this triangle are similar. They have the same angles, and this is a right angle triangle with A, and this is also a right angle triangle with A. So in actual fact, we can use this fact to figure out the length of this whole vertical part here, because we know that the length of, say, this part is equal to this expression here, and we want to find the length of this part here. And basically, since this triangle is similar to this one, we notice that the hypotenuse is sine B instead of 1. So that means this side has to be sine A sine B here. And this green portion must be cosine A sine B. And of course, sine A plus B is going to be the sum of the green and pink lengths. Or, in fact, it will be equal to cosine A sine B plus cosine B sine A, which is what we got at the beginning. If I would like to scroll up. That's how we get this identity here. And we can get cosine A plus B from the same triangle. Notice that we have cos B cos A here is the whole length of this triangle, and we know that this little part here is sine A sine B. We know this length here is sine A sine B. And so if we want to find out this final length here, which will actually be the horizontal of this entire triangle with the radius 1 and the angle A plus B, this length here is going to be equal to cosine A plus B, or rather, it will be this total length minus this portion, or cos B cos A minus sine B sine A. And this is essentially how you get the two identities that we can use for problem solving here. Now, why are these identities useful? There's a kind of problem that comes up in these further period examinations fairly often. And for example, it could be something like find sine 3 theta, or show that sine 3 theta is equal to yada yada yada. And basically, using our two identities that we figured out, we can make A and B equal to different amounts of theta. For example, we know that sine 3 theta is sine 2 theta plus theta. So our A is 2 theta and our B is theta. And we also need to find out some sine and cosine values for 2 theta. And to do that, we can use the fact that sine 2 theta is equal to sine theta plus theta, where our A is theta and our B is theta. So first we can work out sine 3 theta is going to be from our identity at this top, where A is 2 theta, we have cos 2 theta sine theta plus cos theta sine 2 theta. So I'm going to sort of rearrange that a little bit, but you get the idea. Sine 2 theta cos theta plus sine theta cos 2 theta. And what do we do from here? Well, we need to find sine 2 theta and cos 2 theta. So firstly, sine 2 theta is going to be, taking it as sine theta plus theta, it's going to be sine theta cos theta plus sine theta, cos theta. And why are these expressions the same? That's because a and b are the same, where this is a and this is b, even though on the other side this is b and this is a. Since a and b are the same, you just get the same expressions on both sides. And so sine 2 theta is equal to 2 sine theta cosine theta. And secondly, to find cosine 2 theta, you have cos b cos a minus sine b sine a. And if both a and b are theta, you just have cos theta times cos theta minus sine theta times sine theta. Or you might recognize that it's cos squared theta minus sine squared theta. So this is equal to cos theta minus sine theta, or cos squared theta minus sine squared theta. And often in questions, you'll be asked to prove that this is really equal to, I think it is 1 minus 2 sine squared theta. And basically, you just have to use the fact that cos theta is equal to 1 minus sine squared theta from the identity that I might have talked about in an earlier video. Sine squared theta plus cos squared theta equals 1. And so you have 1 minus sine squared theta, which evaluates to 1 minus 2 sine squared theta. And remember, we got to keep track of our original goal. Our original goal is to find sine 3 theta. And now we found the values of sine 2 theta and sine cos theta that we can use to get our final sum. So if we replace sine 2 theta with 2 sine theta cos theta, and then that is of course multiplied by cosine theta, plus sine theta times cos 2 theta, so that would be sine theta times 1 minus 2 sine squared theta. And how would we do this? Well, we have 2 sine theta, cos theta, plus sine theta, 1 minus 2 sine squared theta. So of course this side becomes 2 sine theta cos squared theta, plus sine theta minus 2 sine cubed theta, because it's sine squared theta times sine theta. And this is just a helpful way to remind you that if you have sine and then a number, which is acting as a power, theta, it really just means sine theta, and then the whole thing is squared. But the number here is just put in front of the input. Like it's put in between the input and the name of the function. And that's sort of the notation that will be used in the further peer exams, but that's basically how it is. And you have 2 sine theta cos squared theta plus sine theta minus 2 sine cubed theta is equal to sine 3 theta. And now this is just going a bit of the extra step basically, but often the exact same question comes up on further peer exams, and it's find sine 3 theta in terms of sine theta. And the way you do this is you make one final substitution with the fact that cos squared theta is 1 minus sine squared theta. So you have 2 sine theta times 1 minus sine squared theta plus sine theta minus 2 sine cubed theta. And to complete our challenge, to complete the question that always comes up, I've done a lot of papers and this question is really, really common. They want you to find sine 3 theta, so we just multiply these brackets out. We have 2 sine theta minus 2 sine cubed theta plus sine theta minus 2 sine cubed theta is equal to sine 3 theta. And finally, we have our answer, which is 3 sine theta, adding up the 2 sine theta and regular sine theta, minus 4 sine cubed theta is equal to sine 3 theta. And that's how you would solve this kind of question. Because this question is like a free 5 marks if you know how to do it. That's 5% of the test, absolutely free, as long as you know how to use these two identities, which are so crucial. Right, so in the next video, I'm going to be talking about how we can change this to sine a minus b and cosine a minus b, as well as the identity for tangent a plus b and tangent a minus b. Alright, so hope you enjoyed this video. Thanks for watching.